In this video, we are going to discuss on the magnitude of electrophilicity and nucleophilicity. In the earlier video, we have discussed the different types of electrophiles and nucleophiles. I have given that here. Benzene, carbene and nitrene. I mentioned they are special type of species. Then for nucleophile, I give three types. They are here: negatively charged species, atom which has lone pair of electron and multiple bonds. For electrophile, I have given another three types, that is carbocation with a positive charge. Second one, carbon which has more electronegative atom attached to that through single bond, double bond or triple bond. Third one, alkene with electron withdrawing group. In this video, we are going to learn what will be the magnitude of this electrophilicity and nucleophilicity. In other words, which species will have higher electron density or lower electron density. So that we are going to learn now. Here I have given in the decreasing order of their electron density. In other words, I can say I have given in the decreasing order of their reactivity. That means these species, benzene, carbene, nitrene, they are highly reactive. They won't exist as such in the molecule, and in fact we cannot separate them. Then we have carbanium or negatively charged species. They are also highly reactive. Then afterwards lone pair of electron, then alkene, alkyne and aromatic ring. So these things, they are not that much reactive and they exist in the molecule as such. But this negatively charged species, they will not exist. Even if they exist, they will be highly reactive. Similarly, this carbocation, it is highly reactive. We cannot separate that. But this thing, carbonyl group, nitrile, halide and imine, we can separate them. They are somewhat stable. Last one, alpha, beta unsaturated system. So I have given roughly the decreasing order of their reactivity or the decreasing order of their electron density. There are two important concepts in organic chemistry which discuss about the electronic property in the molecule. The first one is nothing but resonance. Consider three atoms like this. I have taken A, B, C. If there is a minus charge on this, there is a double bond. Afterwards, the atom C, we have minus charge. Then this may fall here and what we get is A minus. This is called resonance. Not only minus charge, it may be positive charge also. Carbocation. Then this bond will fall here and what we get is A plus. Remember, the arrow always should go from the nucleophilic position to electrophilic position. Another option, even if there is lone pair of electron, then also it is possible. The lone pair of electron may fall like this and what we get is not another lone pair, it is minus charge. Since this atom has lost its lone pair, this will become plus. This plus charge refers that this atom has lost its lone pair of electron. So we get plus as well as minus here. So this is called resonance. Generally, what we draw the resonance structure will be based on this. One minus charge migrates, another one plus charge, that is fulfilled by a double bond. Third one, lone pair of electron involves in resonance. What we get is anion as well as a plus charge. Second one, it is inductive effect. In order to understand that, you should know about electronegativity. If carbon atom is attached to another carbon atom, the two electrons present in this bond is placed in the middle. If carbon is attached to hydrogen, then also the same. The two electrons are in the middle and it is shared by both atoms. But when carbon is attached with nitrogen or with oxygen or with halogen, the electron in the bond, they are not in the middle. These electrons are pulled by the nitrogen atom or oxygen atom or halogen atom, because the electronegativity of nitrogen, oxygen and halogen, they are higher than carbon. But carbon and nitrogen, they have almost similar electronegativity. So what is the electronegativity? It is nothing but the ability of an atom to pull the electron cloud towards it. It may be in the bond or it may be lone pair of electron. So it has the ability to pull that. That is called electronegativity. And this phenomenon is known as inductive effect. Generally, this electronegativity is measured on Pauling's scale. For carbon, it will be around 2.5. Nitrogen around 3. Oxygen 3.5 and fluorine it is 4. So if you see in this period, when you go from carbon to fluorine, the electronegativity increases. You may know that fluorine atom has the highest electronegativity. It is around 4. It is not exactly 4. Approximately it is 4. It increased by 0.5 when you go from carbon to this, nitrogen to oxygen, oxygen to fluorine. It increased by 0.5. Now, let us go to the nucleophile and check how the resonance and inductive effect affect the electron density on that. First, let us go to carbanion. Negatively charged species. First one, carbanion. Next, we have N minus. The carbon valency, it is 4. In that one I have removed, I have introduced minus charge. Similarly, nitrogen, the valency is 3. I have removed one valency and I have put one minus charge. Similarly, for oxygen 2, like this. Now, here we have C minus, N minus, O minus and Cl minus. The electronegativity is higher for halogen. That means the ability to pull the electron cloud towards the atom is more for fluorine. Because of that, the available electron cloud to attack the electrophile become less. In other words, the nucleophilicity decreases. because the available electron density is very less, so it decreases the nucleophilicity. So this is nucleophilicity increases when you go from F minus to C minus. So carbanion has the highest nucleophilicity, then the second one N minus, next alkoxide, the last one halides. But the electronegativity increases in this order. Second one, what about resonance? How the resonance affects the nucleophilicity? Let us go for this. I replace one of the R group with carbonyl group. Like this. Similarly, I replace one of the R group with now it is nothing but ketone, the carbanion generated from ketone. This is nothing but amide and this is nothing but acetate. Now this minus charge can delocalize like this. Similarly, as a result, the available electron cloud on this carbon or nitrogen or oxygen become less. In other words, this carbanion is resonance stabilized. It is more stable than this one. If it is more stable, the reactivity will be very less. So compared to this one, this carbanion has lesser reactivity, lesser electron density because it delocalizes on this carbonyl group also. Further, if I replace two groups with carbonyl group, then what I get is this one. So this compound, it is called active methylene compound, which has two electron withdrawing group or two carbonyl group. So this is active methylene compound. So the anion generated from active methylene compound, and this one it is called imide. If there is one carbonyl group, then we call it amide. If there are two, we call it imide. In this case, it is not possible. What about this? Now this minus charge can involve in delocalization on two carbonyl groups. So because of that, this is more resonance stabilized than the earlier one. Similarly, in this case, it involves in resonance on both carbonyl group. So if you compare this three, the reactivity is high for carbanion. When you go for ketone, it decreases. When you go for active methylene compounds, it decreases further. The reason is it is resonance stabilized. What about the lone pairs of electron? That is the second type of nucleophile. How does it affect? First, let us consider lone pair on nitrogen, oxygen and fluorine. This has one lone pair of electron, oxygen has two, fluorine has three lone pairs of electron. Which one is more nucleophilic? The electronegativity is high for halogens and low for nitrogen. That means the available electron cloud on this atom to attack the electrophile is less here and more on nitrogen. So if you see the reactivity, nitrogen is more reactive than fluorine. The reason is electronegativity. Because of electronegativity, the available electron density on that atom is less. Now let us go for a resonance. Let us consider like this. Now let us consider these two compounds. Now this lone pair of electrons can involve in resonance and it can go like this. As a result, what we get is so you can see here I have got positive charge and minus charge on this. Similarly, like this. Now, what about the nucleophilicity of this lone pair of electron? You can see clearly in this, the lone pair of electron is not available on nitrogen or oxygen. So this cannot act as nucleophile. When the lone pair of electron is in resonance, the nucleophilicity of this group has got decreased. In fact, in this system, what we call enamine, which has electron withdrawing group, this nitrogen cannot attack the electrophile because the lone pair is not on nitrogen. It involves in resonance and the electron density got decreased and the nucleophilicity is lost. Third one, multiple bonds. Let us consider this ethylene and vinyl chloride, propene. Now, which one will have higher electron density? Which one will react faster with the electrophile? I have three compounds. Which one will react? Which one will attack the electrophile faster? Here, this chlorine has higher electronegativity. It tries to pull the electron cloud from the alkene. So because of that, the electron density on this alkene is less than this one. In this, there is no group, no atom to pull the electron density. So compared to this, the electron cloud or electron density is less on this group, on this compound. On the other hand, this CH3 can give some electron density to the alkene. So because of that, this has higher electron density than this. So if you go for the increasing order, the first one will be this. It has the lowest electron density because of the higher electronegativity of halogen atom. Second one will be like this one because there is no group to give or to remove the electron density. Third one is this. So this is highly nucleophilic than this or this one. What about resonance? So this is based on electronegativity. Now we are going for resonance. I go for the same compound. I attach this like this, say a carbonyl group. Now this double bond involves in resonance, and what we get is, sorry, it is O minus this one. So the electron density on this has been removed. Now this position is electrophile. This position is electrophile now. So we have discussed about that in the types of electrophile. So when I attach an electron withdrawing group, the electron cloud is being removed and we get electrophile there. I go for one more category, that is methyl vinyl ether. What about this? Here we have lone pair of electrons. It involves in resonance. As a result, what we get is this one. It is just reverse of this. When I attach an electron withdrawing group, I got positive charge there, but when I introduce electron donating group, I get negative charge on this. So the electron cloud here has got increased, but here it got decreased. The order, so this will be the lowest one, this is second, and this one third. The same concept, it can be applied to aromatic ring also. I go for this. Now you can compare this part, whatever I have shown earlier. Now I just add two more double bonds. Now this is aromatic ring. So this particular portion is nothing but methyl vinyl ether, and this is methyl vinyl ketone, similar to the one whatever I have discussed. So because of the resonance, what I get is positive charge. So it increases the electron density on this atom. But in this aromatic ring, it is further in conjugation here. So what we get is another resonance structure in which the minus charge is on this carbon. So we get minus charge on this carbon as well as this. If you go further, you will get on this carbon. Basically, the electron cloud on the ortho and para position has got increased. So now this can attack the electrophile and we will get the corresponding product. So product, whatever we get, will be like this. So we get ortho product and para product. That's why we call this OMe group is ortho and para directing. The reason is the electron density on that position is very high because of resonance. What about this? This pulls the electron from here, and what happens is the electron density on this carbon got reduced. So this carbon cannot attack another electrophile because this also plus, this also plus. The attack of this is not possible. In the earlier case, there was minus charge. It attacked the electrophile easily. But now this plus and this plus cannot react. Then further I go for resonance. What happens? I get positive charge here. So again it cannot attack. So this system cannot attack the electrophile from the ortho carbon and para carbon. This carbon and this carbon is not nucleophilic. It is electrophilic in nature because of the resonance. But what about this carbon? The metacarbon. The resonance has not affected the electron density on this metacarbon. So the electron density or electron cloud on this carbon is equal to that of benzene. Because it has not been affected, it has not been touched by the electron withdrawing group. So now this can attack electrophile. So this carbon can attack electrophile to give the product. So what we get is a product like this. Since it is in the meta position, we call it this carbonyl group is meta directing. Listen carefully. In the earlier case, methoxy group increased the electron density on ortho carbon and para carbon. But in the second one, the electron withdrawing group decreases the electron density on ortho carbon and para carbon, and the meta carbon is unaffected. That attacks. The electron density on this carbon is not increased by this group. It remains unaffected. On the other hand, ortho carbon and meta carbon, in that two position, it got reduced. In the next video, let us discuss what will be the effect of the resonance electronegativity on electrophilic species.